Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss potential calculation in different simple cases. Let's begin. There are two types of charge distributions. When the charges are discrete and when the charges are in continuous manner. If the charges are distributed discretely, so here we calculate the potential at a point due to a number of point charges. How to calculate the potential here? Let we consider Q1, Q2, Q3, Qi, Qn are the point charges at distances, that is the distance at r1, Q2 distance at r2, Q3 at a distance r3, Qy at ri, Qn, Rn from the point P. So, we have to calculate the potential at point P due to these point charges. First we calculate the potential at point P due to the charge Q1. At that case, we assume that all the charges are absent. That's the basic point. When we calculate the potential due to a particular point charge, the another charges are assumed to be absent. So here we calculate potential at point P due to charge Q, due to charge Q1, assuming all other charges absent, be absent. Let that potential at point P1 P due to the charge Q1, let V1, that is 1 by 4 pi epsilon naught Q1 divided by R1. Similarly, the potential at point P due to the charge Q2, Q3, Qi and Qn like this. Similarly, potential at point P due to the charge Q2, that is written as V2, 1 by 4 pi epsilon naught Q2 by R2 up to Vi 1 by 4 pi epsilon naught Qy by Ri up to Vn 1 by 4 pi epsilon naught Qn by Rn. V1, that is the potential due to the charge Q1 at point P, V2 potential due to the charge Q2 at point P, like this. Now the total potential at point P due to the charges like Q1, Q2, Q3 up to Qn, we have to add these potentials. So here we write, therefore total potential at point P due to charges q1, q2 up to qi up to qn, the total potential is given as, that is V is equal to V1, V2 up to Vi up to Vn. Therefore V, when we add these potentials, here we take the term 1 by 4 pi epsilon naught as common, 1 by 4 pi epsilon naught as common, and the charges are q1 by r1, q2 by r2 dot dot dot, qi by ri plus dot dot dot, qn by rn. That can be written in the way of summation. So total potential V due to these charges 1 by 4 pi epsilon naught summation over I is equal to 1 to n qi divided by ri, and the total potential at point P due to the number of point charges, and the point charges are distributed discretely. Now the another aspects, if the position vectors are like in this manner, let we take the coordinate axis, here be the coordinate axis O, x, y, z. The position vector of the charge q1 be r1, charge q2 let r2, like that of charge qy be ri and charge qn be rn. These are the position vectors of the respective charges from the origin. Let you take a point P which has the position vector r vector, position vector r vector, these are the vectors, position vector r vector from the origin O. Let r of I is the position vector of the charge qi from the origin. This is the at point P, that is the position vector r, and the qi charge exists at the position vector ri. Now the magnitude of relative position vector of the point P with respect to the charge qi, the magnitude of the relative position vector of the point P with respect to the charge qi, the distance will be how much? That is r minus ri magnitude, that is the position vector of the point P with respect to qi. Therefore right here the potential at point P due to the charge qi, here we write the potential, therefore potential at point P due to charge qi, that is Vi, since that is the magnitude of the relative position vector of the point P with respect to the charge qi, that is r vector minus ri vector magnitude. So the potential at point P due to the charge Qi will be 1 by 4 pi epsilon naught the charge be Qi divided by its distance, that is r minus ri vector magnitude. So the total potential at point P due to all the charges like Q1, Q2, Qy, Qn like this will be how much? We have to summing all these three, all n number of charges. Hence total potential at point P due to all the charges, that is V is equal to summation over I from 1 to n 1 by 4 pi epsilon naught Qi divided by r minus ri vector magnitude, r vector minus ri vector magnitude. That can be written the total potential at point P due to all other charges. Total potential V is equal to 1 by 4 pi epsilon naught summation over I is equal to 1 to n Qi divided by r minus ri vector magnitude and the total potential. Here the total potential at point P due to all other charges, again the total potential point P due to all other charges. When these charges are discretely arranged or discretely distributed, if these charges are continuously distributed, then what should be the potential at a given point? Another aspects to calculate the potential, that is electric potential due to a continuous charge distribution. Here we consider a continuous charge distribution having the charge q. Let here the charge is distributed continuously and the amount of charge be q. Q amount of charge is distributed continuously. Here we take the coordinate plane, x, y, z. Let P be a point with the position vector r. OP is equal to r vector. Let us consider a small element having the charge dq, small element having the charge dq, that is the position vector r dash from origin O. The displacement vector from charge dq to the point P, that is the displacement vector. The displacement vector will be how much? R vector minus r dash vector, r vector minus r dash vector as the displacement vector. So at point P we have to calculate the potential due to this charge element dq. Now potential at point P due to the charge element charge element dq, that is dv is equal to 1 by 4 pi epsilon naught dq divided by r minus r dash magnitude at the distance. Here the charge distribution is of three types. Continuous charge distribution is of three types. One is linear charge distribution, another one is surface charge distribution, and last one, that is the volumetric charge distribution. In this way, we calculate three different conditions for the total potential at point P due to these various types of charge distribution. First one, if the charge distribution is linear charge distribution with, we take the technical term, that is linear charge density, that is lambda. Linear charge density means charge per unit length. Lambda, that is charge per unit length, which is equal to, for continuous charge distribution, dq by dl, or dq is equal to lambda dl. Now putting that particular value in that of expression, we get, therefore the small potential will be how much, 1 by 4 pi epsilon naught lambda dl divided by r minus r dash magnitude. But the total potential at point P, when the charge distribution is linear, then that particular sum can be integrable. So the total potential, since the charge are distributed continuously, that sum changes to integration. Then total potential at point P due to whole of linear charge distribution, it is V is equal to 1 by 4 pi epsilon naught integration over L, linear integration, lengthwise integration, lambda dl divided by r minus r dash magnitude, as the total potential at point P due to the linear charge distribution. Charge is distributed linearly. Again, if the charge is distributed surfacely, surface charge distribution. Second one, here we take the second one. If surface charge distribution in the surface wise, if surface charge distribution then surface charge density sigma, that is charge for surface area, charge per unit surface area, So here sigma is equal to dq by ds. ds is the unit surface area. So charge dq is equal to sigma ds. Therefore dv is equal to 1 by 4 pi epsilon naught sigma ds divided by r minus r dash magnitude. Again total potential V is equal to 1 by 4 pi epsilon naught, that change to the surface integration over that surface S sigma ds divided by r minus r dash magnitude. For continuous charge distribution, the summation is changed to integration, that is the total potential at point P when the charge is distributed surface wise. Third one, for volume charge distribution, for if volume charge distribution is taking into consideration, then volume charge density rho is equal to charge per unit volume, charge dq per unit volume, let dv. So dq is equal to rho dv. Therefore the small potential element dv is equal to 1 by 4 pi epsilon naught charge in place of charge, that is rho dv divided by r minus r dash magnitude, and the total potential V is equal to 1 by 4 pi epsilon naught, that is volume integration over the volume V, rho dv divided by r minus r dash magnitude. That is the expression for total potential at point P when the charge is distributed volumetrically. These are the different aspects for the calculation of potential calculation, different simple cases. When the potential at a point due to the number of point charges, when the point charges are like this, that is the expression. When the point charges are like that manner, that is the expression for total potential. And when the charge is distributed continuously, continuous charge distribution, charge distributed linearly, total potential, charge distributed surface wise, total potential, charge distributed volumetrically, volume wise, that is the total potential at point B. Any point of considerations, we calculate the total potential according to the distribution manner of charges. So with this useful and informative notes, let me wind up this session. Thank you.